So after we get this differential equation, we can change it to this form. So we are having it as dA over dt plus a function p of t times a is equal to 600. This can be treated as q of t according to a linear equation. Since this is in a standard form, we can apply the integrating factors method, and you will end up with a of t as this one. So this is the amount of salt at any given time t for tank 1. And to proceed to the particular solution, we need an initial condition. Initial condition is directly not given in the problem, but we can get the initial condition indirectly by just looking at the problem. So we know that at time t is equal to 0, tank 1 is not going to have any salt in it, right? So it has a concentration of 0 gram per liter. So the amount of salt at time t is equal to 0 can be written as A of 0, and the amount of salt is 0. So you can do A of 0 is equal to 0, and when you solve for the problem, you will end up with this to be your amount of salt at any given time t. So this is how you do for tank 1. So if they're asking only one tank, it's pretty easy to evaluate. So now what we are going to do is we are going to go to tank 2. And I forgot to mention one thing. So over here, we found that at t is equal to 100 minutes, the tank is going to be emptied. So when they're asking something to be found after t is equal to 100, like let's say at 2 hours, at 120, this equation might not be valid because there's nothing in the tank, so your volume is directly going to go to 0. I can't say that the equation will be invalid, but the behavior of the amount of salt would change a lot. So now I'm going to tank 2 now, and I'll evaluate the same process again for tank 2. Over here, what is going to change is the amount that comes in tank 2, or the rate. Let me put rate, that's much better. So the rate that comes in tank 2 is the same as the rate that exited tank 1, right? Because we know that the water is just going to come from here to tank 2, and whatever this is, it's the same as what came from here when exiting. So that is how we are going to start off this problem with. So our rate in for tank 2 is going to be, I'm just using the subscript 2 for tank 2. Okay. So the rate in for tank 2 is going to be the same as that. So we'll be using 4A over 100 minus T. And we know A, and we have already evaluated it. So I'm going to use that directly. And when you do the calculation, you'll end up with the value of 800 minus 100 minus T cube over 1250. I'm skipping through the calculations and also the integration in the previous step because this problem is pretty long and I want to cover the concept more than solving. If you have any doubt with solving the integration factor method, then I would advise you to go back and look at my video on the linear differential equation solving. So now we can continue, and we know the rate at which it comes in now, and now we can find the rate at which it exits. So the rate out is going to be 40 liters per minute. That's the volumetric rate at which it exits. So 40 liters per minute. Okay, and we need grams per liter. Over here, you can't use 50 grams per liter. It's the same case as what happened in the rate out over here. So you're going to do the same way as what you did there. So your gram, the concentration gram is not the same as A of t anymore, because it's tank 2, it has different conditions. So we use B of t here to represent for tank 2. And how much volume goes out over here? Over here, it's going to be 1000 plus 40t, because it enters at 40 liters per minute. So it's 40t and it exits at 40 liters per minute. So again, the volume exiting is 40t. So it's going to be 1000 plus 40t minus 40t, which is just 1000. So I'm just simplifying it and writing 1000 grams per liter directly. So when you do this, you'll get B over 25 grams per minute. So again, we're going to apply the same thermodynamic law, and we're going to get the differential equation as dB over dt. This is the change in the amount of salt for a given time for tank 2 or tank B. That is equal to the rate that comes in, that is 800 minus 100 minus t cube over 1250. That's the rate coming in minus the rate going out. So again, what we can do is we can move the B over 25 to the left hand side, and then your P of t is going to be 1 over 25, and your Q of t is the entire right hand side. That'll be 800 minus 100 minus t cube over 1250. So since you know your P of t and Q of t now, you can use the integrating factor method and you can find B of t. I'm not going to do the solution for you now, but I would highly encourage you to do it and come up with the solution. So we get a constant over here, and we need an initial condition to come up with the value for the constant. So if you look carefully at the problem again, you're going to use the same trick and say that initially at time 0, we can say that B of 0 is equal to, we have the concentration at time is equal to 0, which was 50 grams per liter. And how much salt was there? Like there were 1000 liters of water, and in each liter there's 50 grams of salt. So we're going to multiply this one by 1000 to get the initial concentration of the amount of salt that was present. So if you do that, you'll be getting 50,000 grams. So your B of 0 is going to be 50,000, right? So this is how you'll be solving it. So you're going to put this 50,000 back in your equation wherever C was there, and you can get a value, or you can get an equation for what B of t is. So if the question asks you further to find the concentration or the amount of salt in tank 1 and 2 after a period of time, let's say 40 seconds or 5 minutes or whatever it asks, so you can just plug in t is equal to, let's say 40 minutes means you plug in t equals to 40, and whatever answer you get would be B of t, provided you do it correctly. This is how you're going to solve this. So there are two major things that you should remember when doing this problem. One of them is you should be using the conservation law, and it's better to state the conservation law before this statement over here, before this line. It's better to say that according to the conservation law, the rate coming in minus rate coming out should be the rate that is present within the system. So we are assuming the conservation law, and we are not assuming, and we are assuming that there is no other loss, right? So whatever comes in minus whatever goes out, the exact amount of the difference is going to be within the tank. That's what we are assuming here. And we are also solving this problem, and when you come to C, you should be careful again, because you have to go back to the problem and you need to look up the values, and then from there you need to get your answer. So that is the next important part of this problem. And finally, since it's a huge problem, you have to do everything without silly mistakes. This is one of the toughest problems in modeling the differential equations. So if you're able to do this problem, you'll most likely be able to do the other problems as well. So there can be questions of the same concept, but just the other way around, like laws of thermodynamics, like heat coming in minus heat going out is the heat present within the system, or they can just use the rate of heat coming in minus the power going out would be the change in internal energy with respect to time within the system. These are all questions of the same concept, but just worded differently. Other than thermodynamics, there can also be questions about interest rates and stuff, borrowing loans and then repayments. Regarding that, there can be questions with how much money you're going to repay for 1 year of time. Questions like that can come up. So this is what modeling differential equation is. It's nothing new. It's just reading the problem, understanding it, and making the best possible answer from your side.